Hello, everyone. My name is Giacomo Beccari. I would like to welcome you to the new event of the ESO Hypatia Colloquium 2022. This is just to remind you that this is a series of events organized to give visibility and to give a platform for visibility to early career astronomers. So we are very happy to host today two talks. And just a very quick technical reminder from my point that the event is hosted on Zoom and broadcast on YouTube. So if you are people attending the event on Zoom, if you are not happy to be part of an event that is broadcast on YouTube, then we ask you to please leave the event. But you can still, as I said, follow the event on YouTube, or even later the event is all the events, this one and any other event of this year, last year, all host and in a playlist on the YouTube channel of the Hypatia Colloquium. You can make questions either so that each talk will last. So each of the two talks will last a total of 30 minutes, which is 25 minutes of talks plus questions. The questions can be done if you are on Zoom. You can raise your hand, and that would be nice. Then you can make the question yourself, or you can type the question on the chat. While people on YouTube, they can, of course, only use the chat, but please post the chat, the question there, and so the speakers can answer it either live or later if the time is over. Then they can still see the question and answer later. Today we have two chairs helping us, Lukasz and Dominika. Lukasz and Dominika, they are fellow and students here at ESO. We are very happy to have them with us, helping us to chair this session. So I think I can pass the word directly to Lukasz for the introduction of the first speakers. And thank you very much, and see you later.
Yes, thank you, Giacomo. My name is Łukasz Tychoniec, and I'm an ESO research fellow here in Garching. And together with Dominika Itrich, a PhD candidate also here in ESO Garching, will be chairing this session for you. And it's my pleasure to introduce the first speaker, Clémence Fontanive, a CHSH fellow at the Center for Space and Habitability at the University of Bern in Switzerland. Clémence obtained her PhD in the Institute of Astronomy at University of Edinburgh in Scotland, and her work focuses on detection and characterization of giant exoplanets and brown dwarfs using observatories including VLT, Hubble Space Telescope, and with particular focus of constraining the demographics and atmospheric properties of those objects. So a final reminder before switching to our speaker, let me just remind you that you can put your questions in a Zoom or YouTube chat. And if you want to ask your question yourself, then please wait to the end of the talk and raise your hand on Zoom. And with that, I would like to give the floor to Clémence.
Thank you very much. Share my screen. All right, is this working? Take this as a yes.
Yes, perfect.
Perfect. Great. Yeah, so thank you very much for the introduction. Thanks a lot for the opportunity to tell you a bit about my work. So I work on a pretty large diversity of things, but today I'm going to tell you a bit about some work I've been doing on planets in binary star systems, and in particular trying to understand how binary star companions can impact planet formation or evolution. So I will actually be talking about a pretty wide range of astronomical objects in this talk. So I just wanted to start with a quick recap of what they are. So I think we're all pretty familiar with stars. So here we have the sun from our own solar system. Mud stars out there are actually smaller than the sun. So they're smaller red M dwarfs like this. And then at the very other end, we have planets. So for example, this is Jupiter, the largest planet in our solar system. And in the solar system, we don't really have anything between stars and planets, but there are this class of objects that are in between, which are called brown dwarfs. So brown dwarfs essentially bridge everything between the biggest planets and the smaller stars. Most of them are found in isolation, but here I'm exclusively focusing on brown dwarfs as companion to small stars. And actually, I'm considering brown dwarfs and planets as the same population. So I'm considering brown dwarfs as an extension of the planetary population as small things around stars. And then, as you probably guessed from my talk title, I'll also be talking about binary systems. And in terms of planets in binaries, there's two different types of planet in binary star systems. And in the context of this work, I'm exclusively talking about what we call S-type planets or circumprimary planets. So this is a system where we have a planet or a brown dwarf that is orbiting its host star, so one star, and then around this star-planet system, there's another outer binary star companion. And these should be distinguished from P-type planets or circumbinary planets, which are systems where a planet is orbiting two stars in a closed binary systems. So here I'm exclusively focusing on something that looks like this. So we know that about half of the stars in our galaxy are part of binary or multiple star systems. So that tells us that we should really be studying binaries as environments for exoplanets if we want to really obtain an overall picture of everything that's happening with planetary populations and planet formation processes. But unfortunately, despite this, historically, binaries have been mostly ignored and very much neglected in exoplanet science, so both on the observational and on the theoretical side. And this is mostly because binaries tend to complicate everything. So they make detections of planets harder, they make simulations of planet formation more complicated. So they've both mostly have been ignored so far. There's still been some studies looking at them, and some of the main results that are now generally agreed on exist. So the first one is actually pretty negative for the prospect of having planets in binaries. Is this generally accepted idea that close binarity, so having an outer star companion on separations of maybe a few tens to 100 astronomical units, has a negative impact on planet formation. So we think that these sort of companions would be preventing the formation or the survival of planets. Observationally, we see this through a lack of close binary companions for planet hosts, which is the deficit that you can see here. So comparing the binary separations of planet hosts in red to the average star field population in blue, and with fewer host stars that are binaries on these sort of separation scales. And then we also see this through the fact that disks around stars tend to be less frequent for tighter binaries, as you can see here. While for wider binaries, we have similar disk fractions as around single stars. And these disks that we find around stars are essentially the reservoirs of material that's available to build planets. So having fewer disks or less massive disks around these close binaries is going to be negative in the context of planet formation. Then there were also some slightly more encouraging results with this idea that slightly wider binaries on sort of solar system scales of 100 or few hundred astronomical units could maybe help with planet migration. So for example, mechanisms like the Kozai lid-off mechanism, which is when an outer binary companion can drive an inner planet on a very eccentric orbit, such that eventually it passes so close to the star that it will then tidally circularize and stay very close to a star. So these sort of processes are often invoked as possible explanations for how giant planets that form a bit further out can reach their observed hot Jupiter orbits. And then finally, what was probably the most promising finding in terms of planets in binaries was indications from really early years, very early on in exoplanet science, that high mass and closing giant planets like hot Jupiters might be predominantly seen in binary star systems, and that these sort of planets may have different planet properties than the rest of the planetary population. And based on this, during my PhD, I conducted a survey to try to put some more robust constraints on this. And we confirmed that most stars that host a very massive planet or brown dwarf on a close separation, so in this case, stars with a planet or brown dwarf above 7 Jupiter masses within a 1 AU separation, we found that 80% of these systems have an outer binary star companion, which is much higher than we would have expected from the average stellar field population. So there definitely seems to be something going on with these sorts of high mass and closing planets being in binaries. So then to try and better understand the effect of multiplicity on exoplanet demographics as an ensemble and put these results into a broader context, I gathered a large compilation of over 1,300 planets that are all within 200 parsecs, organized in around 938 host stars, a wide diversity of hosts. And I searched for outer binary companions to all these systems, so using any available information I could find in the literature and the Gaia catalogs. So we found 218 of our planet hosts to be in binary or higher order multiple systems, with again a pretty wide range of outer binary companions. And we published all of this last year. I only have time to highlight a few aspects of this study now, but what I will present is essentially how we can use this compilation to look at trends in planet properties as a function of host star multiplicity. So this plot here is showing all the planets and brown dwarfs that we have in our sample. So plotting the planet masses as a function of its semi-major axis, where we have all the systems that were found to be in binaries shown in red, and then those that were found around single stars or apparently single stars are shown in blue. And we can essentially use this to investigate how or if host star multiplicity affects planet properties for various regions of the parameter space, which we divided with these sort of arbitrary thresholds over here. So the first thing that we can do is to take some mass slices in this plot. So looking at different horizontal sections and comparing the planet's semi-major axis distributions between the planets that are in binaries and those that are in single stars. And if we start at the bottom here and look at the small sub-Jovian planets, so all the smaller rocky planets that are less than 0.1 Jupiter masses, you can see that we're essentially seeing no differences in the semi-major axis between those that are in binaries and those that are around single stars. If we go a bit higher up in mass and look at the core of the giant planet population, we start seeing this double peak distribution. So this is due to the fact that we have the hot Jupiters that form a first population at small separations, and then at wider separations, so around the small line at a few AU separation, we have this secondary bulk population of giant planets. And you can see that we start having this slight overdensity of giant planets in binaries for this short separation population, so for the hot Jupiters. And as we go higher up in masses, so looking at the very most massive planets and brown dwarfs, we essentially find that almost all the high mass planets and brown dwarfs that have very short orbital periods are found to be in binaries. And this is fully consistent with the previous results that I mentioned before. So then we can do the same thing by taking some vertical slices in this diagram and looking at the planet mass distributions as a function of whether the planet is in a single star or in a multiple star. So if you start far out for the really widely separated planets and brown dwarfs, so only direct imaging can detect those, so we can only detect the massive ones. We're not really seeing differences between those in binaries and those in single stars. If we get slightly closer in and again look at this bulk giant planet population here, we're still not really seeing any differences. And as we get closer in, we once again have a double peak distribution. So this time is due to the sub-Jovian planets from this first peak here at small masses, and then the hot Jupiters and brown dwarfs from the secondary peak. And you can see that again, we have this overdensity of high mass planets and brown dwarfs in binaries for all the short period planetary systems. So we really have this strong result that shows an excess of high mass planets and brown dwarfs in binaries, with these massive hot Jupiters in binaries showing some larger masses and or some tighter orbital separations. So now the question is, what is actually going on with these systems? What is special about either these planets or the binary systems that they are in? So what we can do is to look in more details at the type of binaries that these planets and brown dwarfs are in, to see if, for example, binary separation might be influencing the underlying planet population. So here we're looking at the planet semi-major axis and planet masses for all the planets and brown dwarfs in our compilation that are above 0.1 Jupiter masses and within 0.5 astronomical units. And we divided those that were found to be in binaries into 3 separate binary separation bins. And we can look at the planet properties as a function of the type of binary they're in. So in the yellow curve, we have the planets that were found to be in the tightest binary systems of less than 250 AU. Then in red, we have the slightly wider binaries out to 1,000 AU separation. And in blue, we have the really, really wide binaries beyond 1,000 astronomical units. And then the dotted black line shows the rest of the planets in this part of the parameter space that were found to be around single stars. And the first thing that we notice here is that the planets that are in really wide binaries have the same masses and semi-major axis as the planets that are around single stars. So the blue and dotted black lines are essentially the same in these two plots. So that tells us that these extremely wide binary companions don't really seem to influence the underlying planetary populations. However, we're finding that the excess of high mass and close-in giant planets and brown dwarfs that were found to be in binaries pretty much all seem to be in binaries on these sort of separation scales of a few hundred AU separation. So that tells us that these sort of outer companions may actually be impacting the resulting planet properties. And in fact, it looks like when we have an outer companion on these sort of separations, we end up with a more massive and or closer in planet to brown dwarf compared to the classic hot Jupiter that we have around single stars or these really wide binaries. So what we're finding is that binaries on separation scales of a few hundred AU seem to be playing an important role in either the formation or the evolution of these high mass and short period gas giant planets and brown dwarfs. So now the question is, how are these binaries actually helping with formation or evolution of the inner planets? What are they actually doing? So in terms of planet formation, there's two dominant channels to form planets around stars. So the first one is core accretion. So this is the mechanism that very likely formed the solar system planets. So it's kind of a bottom-up process where we start coagulating small planetesimals or pebbles to form a rocky core. And then eventually, if it gets big enough, it can start attracting a thick atmosphere and become a giant planet. So this mostly forms small planets on the order of what we have in the solar system, potentially a bit bigger than Jupiter, but not much more than this. And in particular, core accretion has a very strong dependence on metallicity to be able to form very massive planets. So only metal-rich stars will be able to form a very massive giant planet, so of a few times the mass of Jupiter, through core accretion. And then the second pathway that we have to form planets around stars is through gravitational disk instability. So this is more of a top-down mechanism, which is a bit more similar to star formation itself. So the idea is that we have these disks around stars, and sometimes if the conditions are right, they can become gravitationally unstable and collapse onto themselves and form massive planets for brown dwarfs. And in general, just from the nature of this process, gravitational instability will form very, very massive planets, and most of the time things that look like brown dwarfs. And there's no metallicity dependence to form any sort of objects with gravitational instability. So now if we go back to the sort of systems that we were looking at on these high mass planets and brown dwarfs and binaries that seem to have something special about them, there's a few reasons to believe that they may have formed through gravitational instability as opposed to core accretion. So the first one being that we're essentially only seeing these trends with multiplicity for the most massive planets, so from several Jupiter masses and up into the brown dwarf regime. And these host stars, the hosts of these systems, don't seem to be particularly metal rich. So they follow the same metallicity distribution as the average stellar filled population, while the classic hot Jupiters that are a bit lower mass tend to be around very metal rich stars. So there's a few clues that point to the idea that these planets that I've been talking about may have formed through gravitational instability. So based on this, I approach theorists that work on planet formation through gravitational instability to try to see if we could test this idea. So what we did is that we took the usual 3D smooth particle hydrodynamic simulations of self-gravitating disks around a star. So if we take them in their usual single star environment, so this is looking at disks of different masses, so from 0.1 to 0.4 solar masses, where the host star is 1 solar mass. And if we let these disks evolve in their usual single star configurations, we find that only the most massive disks are able to become gravitationally unstable and collapse to form these little fragments, which are the white dots that you're seeing that are going to become giant planets and brown dwarfs. So this is the known thing. We need a certain disk mass for the disk to become gravitationally unstable and fragment. And with the setup that we use for these disks, this threshold for fragmentation is somewhere between 0.2 and 0.3 solar masses for the disk itself. So based on this, we focused exclusively on this 0.2 solar mass disk, which we know doesn't fragment by itself around a single star. And we try to see if anything changes in the disk evolution if we add a binary companion around it. So we took this 0.2 solar mass disk, and we added a 0.2 solar mass companion at different separations. So in the closest cases, you can actually see the binary companion over here. So initially, we put the binary orbit to be perfectly circular and mutually aligned with the plane of the disk itself. And letting these disks evolve, we found that some of them fragmented and others didn't. So what we found is that at really tight binary separations, the binary companion ends up passing so close to the disk, almost inside the disk, that they completely disrupt the disk. And we end up with essentially nothing left to form planets. And then at really wide separations, we're finding that the effect of the outer binary companion that we introduced didn't really impact the disk. It was too far away to really have an impact on the disk. So we end up with something similar to the single star case. But at these in-between sort of intermediate separations of a couple hundred astronomical units, we found that the disk that wasn't fragmenting before was able to fragment and form giant planets, which was really exciting because this is exactly what we were hoping to find, what we were trying to test. But of course, we then also needed to check that it works in a more realistic range of binary configurations and not just this perfectly circular, mutually aligned binary orbit. So we started by testing binary eccentricity. So now we're looking at, again, binaries on different semi-major axes, but now varying the eccentricity of the binary orbit as well, but keeping it mutually aligned with the plane of the disk. And what we find is that, again, some of them fragmented and others didn't. And what seemed to matter here was actually the periastron distance in the binary orbit. So we found an optimal range for the configurations that worked that is a correlated function along this axis of semi-major axis and eccentricity. So it means that in cases that worked before on circular orbits, increasing the eccentricity means that the companion passes too close into the disk and it erupts it, so it no longer works. But at wider separations that didn't work with the binary that was circular, having a moderate eccentricity can bring the companion close enough that it starts having an impact and it can trigger fragmentation in the disk. But again, if the eccentricity gets too high, it ends up being detrimental to planet formation. Then the second thing that we could test was binary inclination. So again, we looked at different binary semi-major axes, this time varying the inclination of the binary orbit relative to the plane of the disk, but going back to a circular binary. And we again find that some of them worked and others didn't, with again, this trend that is correlating semi-major axis and binary inclination. So what happens here is that cases that didn't work at small semi-major axis on a mutually aligned orbit can start to work if the companion is highly inclined, because it doesn't pass like right into the disk or at the edge of it as often. But on the other hand, at wider separations that worked when it was aligned, increasing the eccentricity decreases the effect of the companion when it's highly inclined. So this no longer works. So we again have this correlated trend for the parameter space that works. And finally, the last thing that we tested was the effect of the outer companion mass. So on top of the initial 0.2 solar masses, we looked at binary companions of 0.1 and 0.5 solar masses. And we found a pretty intuitive result that a larger mass can allow a similar impact from a larger distance. So we found that if we take a smaller companion, it can only really work at a much closer separation. But if we take a more massive companion, we can achieve the same results from a wider semi-major axis. So we have this very exciting sweet spot of binary parameters that can essentially cause an otherwise stable disk to fragment and potentially lead to the formation of some giant planet superdwarfs. And what's really exciting about this is that the range of binary parameters for which we find this to work is perfectly consistent with observations. So we find that it works for separations of a few hundred AU, with the exact range being a function of the different binary elements. And this is the sort of separation scales that we were observing. But it's also consistent with the idea that really wide binaries have very little impact on the disk and planet formation, and the fact that really close-in companions that pass too close to the disk ends up being destructive and prevent planet formation. So all of this is perfectly consistent with observations, and it essentially provides a new potential formation pathway that could explain at least some of this overabundant population of giant planets and brown dwarfs that we see in these type of binaries. And just to summarize everything I've been talking about, so we saw that when looking at exoplanets in binaries, we find that short separation binaries typically prevent planet formation. We see that really wide binaries tend to have very little impact on the resulting planetary systems, but we're seeing that massive close-in planets and brown dwarfs are quite often observed in these intermediate separation binaries, which likely play a role in their existence or their distinct properties. And finally, we have this exciting new result suggesting that these outer companions might be able to trigger fragmentation in disks that would otherwise be stable, and in this way help to form some systems through gravitational instability. So I hope that I managed to convince you that binaries are really interesting and that we should be studying them for many reasons. And I'm happy to take questions. Thank you.
Yes, thank you very much. Virtual clap for you. And I'm going to invite questions indeed. We have roughly 7 minutes for questions remaining, so please raise your hand. We already have a hand raised from Henry, so please unmute yourself.
Yes, thanks a lot, Clémence, for a very nice talk. And of course, I fully agree with you. Binaries are the most important. So I was still unsure because, of course, in your simulations, it is clear that you make planets, but it looks to me that you make planets at a very wide distance from the star, which, of course, seems to contradict your observation, where you see that, in fact, it is mostly the close-in planets that are increased in binary systems compared to normal stars. So how do you reconcile both things then?
Yeah, absolutely. So we haven't quite reconciled the two sides yet. So indeed, GI is essentially forming things at pretty wide separations of a few tens of AU. So we stopped the simulations pretty early on. We haven't yet looked at the evolution of these fragments to see what happens to them afterwards. We would still need some sort of migration to get them inwards to where we observe them. But there are several things that look pretty promising with this. So the first thing is that from the simulations that we have, it looks like the migration rates in the disk might be a bit faster than in usual disks. So that would already be one way that could help push these planets even more inwards than around a single star. And then if they don't migrate through the standard disk migration, I mentioned at the beginning that effects like the Kozai-Lidov mechanism, where we have an outer companion on these sort of separation scales, can also help move companions on really tight separations. And the good news with these systems is that they're forming, by definition, we make them form in a system where we have what we would need for something like Kozai-Lidov to work. So we don't have actual simulations showing that, like how they get there, but it looks like there's a few hints that suggest that it might be even more feasible than around a single star to then move these outer planets on very inwards configurations. But it's something we're going to be working on next.
Okay, and in your simulation, you also see, of course, in several cases that you form many planets, in fact, not only one. So we don't see that, do we?
No, absolutely. So actually, all of these systems that seem to stand out for their configurations in binary is actually single planet system. So this is also something that we need to look into. Maybe with the migration of the planets, some end up being ejected and only one ends up surviving, or most of them end up spiraling into the star. This is something that we need to investigate next, yes. But at the moment, yeah, we're producing many more than we see.
Okay, thank you very much.
Right, thanks a lot. And we have a hand raised from Giacomo, so please.
Yeah, thank you very much. Really fascinating topic. I was wondering, so because one of the beauty of it is that of what you're doing, in my opinion, is that you combine basically binaries and disk evolution and planet formation and stellar evolution, if you want, everything is there, right? So, and I was wondering, do you, in fact, if we look at your result from the disk perspective only, so looking at the evolution of disks, because the evolution of disk in binaries is a big topic as well. So I was wondering, because I don't know about that, but do we have observations of disks in binary system through ALMA, I can imagine, which would somehow capture some of the intermediate stages that you are probing with your simulation. So in other words, that you can compare with your simulation.
Yes, I'm not sure about ALMA surveys. I know that about 10 years ago, there had been a few surveys looking at disks of binary stars in young star forming regions. But they actually mostly focus on really tight binaries. And essentially the results was that for binaries of a few tens of AU separation, this ended up being truncated, shorter lived. So things that are all pretty negative for the prospect of planet formation. The one result that I remember from slightly wider binaries is that actually the mass distribution of the disks is not directly proportional to the masses of the stars themselves. So you can end up with one star having a much more massive disk than it would as if it was single, and the other star having less mass. So it would be harder to form planets around one of the stars, but you would actually put more chances on your side with the second star if it is in a binary. But I'm not sure how big of a sample these results are from.
Okay. Thanks.
Right, thank you. And do we have a hand raised or any questions in the chat? In the meantime, I would like to ask a question myself. Basically, I was also wondering about the irradiation effect, because those simulations are purely exploring the dynamical influence of the binarity, right? But I could also imagine that in a wider binary system, even if the dynamics wouldn't be sufficiently strong to disrupt the disk or to affect the planet formation, what about the effects of the irradiation, external irradiation that it would affect on the disk?
Yeah, that's a good question. We haven't really looked at this in these simulations. And as an observer, I don't really have a good feeling for how that would play. But it's definitely something that several people have raised, and something that would be worth looking at. Yeah, I don't have a good intuition for the effect that it would have on different scales, but definitely something worth looking into. Absolutely.
Yeah, thanks a lot. And do we have any final questions? We have still 1 minute for that. And if not, then I would like to ask one more. So in the instability regime that you basically set for your disks, I mean, this of course seems to be model supported, but the spot that you select for the disks that will become gravitationally unstable, so above certain threshold, I think 0.2 solar masses, right? So
yes, so we saw that the disk of 0.3 solar masses and higher up collapsed.
Yeah, but this is for a specific stellar mass as well, right? It's around one stellar mass.
These are all one solar mass stars.
Yes. So this is explored basically on the solar-like star, right? But
yeah.
Okay. So I could imagine that the effect would be slightly different on a different.
Yeah, exactly. So we expect the disk to roughly scale with the mass of the star itself. So we would probably have smaller disks around smaller, like M-dwarf stars. And actually, it seems from observations, we're not finding many giant planets around M-dwarfs. They mostly have small rocky planets that form through co-accretion, or binary star companions that form through stellar formation. But it seems a bit hard yet to form gravitational instability planets or brown dwarfs around very low mass stars, but it hasn't really been explored as far as I know on the theoretical side as much. Most models are around sun-like stars.
All right, thank you very much. And with that, we can close. So thank you very much again. Thank you for the interesting questions. And we're going to move to Dominika, who's going to introduce the next speaker.
Thank you very much, Łukasz. And Clémence, congratulations for your wonderful talk. And I think I'm quite convinced now that binaries are important. Our next speaker is Rubén Fedriani from Chalmers University of Technology. Rubén obtained his PhD in star formation in Dublin Institute for Advanced Studies and University College Dublin. And currently, he is a Maria Skłodowska-Curie Actions Fellow in Sweden. Today, he will tell us about near-infrared observations with VLT instruments and how to reveal a clustered region of massive star formation. Ruben, the floor is yours.
Okay, so let me share my screen here and hopefully put my slides up. So if you can give me thumbs up or something to see that everything is all right.
Yeah, everything is all right.
Okay, so, well, first of all, thank you very much for giving me the opportunity to present my work here in the Hypatia Colloquium. Thank you very much again. And also, I would like to thank my collaborators that, you know, allowed me to kind of like with their work and stuff to present the work here, and also to the Marie Curie Actions that, you know, has funded my research here. Okay, so without any further ado, let me tell you a little bit about, you know, star formation, massive star formation, and how I have used, or we have used the VLT instrument in ESO to reveal near-infrared jets. So, yeah, but first of all, let me tell you why I think it's important to study star formation, but massive star formation in particular. We all know that massive stars regulate the process of star formation from very early when they form until their death in these massive stars in the form of supernova. During the formation and during their life, they add instabilities in the cloud that they are forming and can even trigger more star formation. And obviously, when they die, they enrich the ISM with heavy metals. However, they are highly challenging both from a theoretical point of view and from an observational point of view. I'm more of an observer, so I'm going to tell you some of the observational challenges that mainly they are located at great distances on the order of few kiloparsecs. They are also highly extended, easily more than 50 magnitudes in AV, and they live fast, right? They are like the rock stars of the universe. They have short time scales, so it's very difficult to catch them. So this is a diagram that has been shown, I think, a few times in the Hypatia Colloquium, but I made a few modifications to try to tailor it for my massive stars, right? So, but for a general view, this is the cycle of stellar birth and death that goes on and on, but basically it starts with a diffuse cloud, molecular cloud, infrared dark cloud, you know, all these kind of clouds that start forming. And through some mechanism that we're not going to get into today, it collapses against its own gravity. There are a few different theories here, but we're not going to touch upon today. But if we zoom in one of the cores here, we can peer into the star and planet formation. I have added here sort of like a naive interpretation of when a star is forming. I'm gonna show you a slide after with the different panels that maybe we're more used to. But basically what happens is that you get, through conservation of angular momentum, this spherical rotating core flattens into a disk, and the star is sort of like accreting material there, and then you go sort of like also a bipolar outflow. Then the cycle continues into the protoplanetary disk system and the Jones system here, the stellar. What happens though, if the mass of the star is more than 8 solar masses that we consider to be massive stars, they end their lives as a supernova, right? So they explode and they enrich the interstellar medium again with heavy elements. So, you know, this cycle goes on, and actually our own solar system might have come from this cycle a few times because we have heavy elements here in our solar system. Okay, so let me tell you a little bit also about the low mass star formation that we believe we understand very well, but then as Clémence showed us, the devil is in the details. So when you zoom in a little bit more in any of these panels, things get very complicated. But in general, we do have a good idea more or less how this proceeds. And again, this is again another version of the previous plot. But you know, if you zoom in into one of the molecular cloud and you go like one of the cores, and again, we zoom in, we have different classes here, but the main takeaway message here is that we have a main accretor, which is the protostar, that is accreting material from the accretion disk. And this accretion powers ejection, all right? So this is the beautiful bipolar outflows that I'm gonna show an image in a second, but also I have also put here like an artist's impression of this process, just also for the general public, that, you know, the material is collapsing, the material is being accreted onto the star from the accretion disk, And at some point here in the movie, you'll see that this is ejection of material. So this is exactly what I am focusing on, this ejection, all right? But before showing you a few images, observation from these protostellar jets, let me also review very quickly high mass star formation, which, as I said, are those stars with more than 8 times the mass of our sun. They explode as supernova, as I told you, and they are super important because they regulate many different aspects of astrophysics, actually. There are 2 main theories. The one is so-called the core accretion, that we can interpret it as an isolated formation kind of thing. So you have one main core here represented with the blue circle here that collapses to form one main star with the outflow and so on. The other theory, so-called maybe like crowded formation, that is the competitive accretion here. You see that you have like a massive cloud here. You have to understand that this is, the scales are very different. This is a cloud scale, several parsecs. And you see that this is collapsing against its own gravity. And you see that it's forming like filaments. And hopefully you can see that there are tiny dots there. Those are formed stars already. And as you can see here, the main difference between the two is that, as the main name says, is that they are competing for the mass. So the most massive star may steal unbound mass from all the protostars. So one of the main predictions also is that the most massive star must be or should be at the center of this cluster. Okay, so these are the 2 main theories. But today I'm going to tell you more about jets, in particular protostellar jets as a tool. Why? Because high mass YSO, this is the acronym here, high mass young stellar objects, are deeply embedded in gas and dust. So direct observation to the star is very challenging. So actually what we see, this is an artist's impression again, we see obscuration way into the center of the star. So we see nothing basically, but still we do see the bipolar outflows, which are a natural consequence of accretion disks. This is just to show you more or less what you should have in mind for the rest of the talk when I'm talking about these systems. We have a main protostar, the main accretion disk, and we have sort of like the secondary envelope that is accreting onto the disk, and then the primary jet being ejected from the star disk system, and then the outflow that we normally understand as a low velocity dragged material from the primary jet at high velocity. Okay, so let me show you one of my favorite images here. That is a low mass protostar actually. It's a HH212 that you see in molecular hydrogen how this beautiful bipolar outflow extends. And as you can guess, the driving source is in the middle here, but you cannot see because it's obscured by the disk and the gas and dust. And this is for low mass, but I can also show you example for high mass that are even more impressive in scale, right? Because this is about 10,000 AU, but when I show you here IDA 13481, the parcel has a scale of almost 7 parsecs. Well, this is depending to whom you talk. If you talk to extra-active people, this is nothing. But if you talk to like planetary people, maybe this is a lot, right? So anyway, to put it in context, if we were to place here Proxima Centauri, and the closest star to the sun, this will be the place. So you see, it gives you a sense how big these ejection of material are. Okay, so since I'm going to be showing you a few near-infrared spectra and tracers, let me spend 1 minute here to tell you what is tracing each of them. So this is a naive impression of a star forming here with the disk, and I have added here a few lines to represent the jet. And we have different tracers, right? Normally, I'm focusing on the near-infrared. One of the most important lines is the so-called bracket gamma. That is a hydrogen recombination line at 2.16 microns. That is a little bit controversial because it may trace the very inner disk wing. It can be also tracing accretion into the star, the jet farther away. So I'm going to show you a few examples now. We have also, very importantly, the CO bandhead. This is the warm CO, the bandhead shown at 2.3 microns more or less. I'm not going to talk about this today, but it's super important again, for star formation. And finally, we've got like 2 super important jet tracers, that is molecular hydrogen and iron forbidden 2. How does it look like, though? When we actually see a spectrum, it looks like this. So We have, as I said, the important Brochet gamma that is tracing activity very close to the star, and this DCO that is very peculiar, the mission that they have. And normally, also when we observe star formation or young stars, we have this rising continuum from warm dust that is emitting in this wavelength. Okay, this is in close to the star, but when we also see the knots, the jet knots from molecular hydrogen, this is what we actually see. So we have here a molecular, well, this is an image, sorry, this is H2 minus continuum. So you see a number of knots there. That is material being shocked against the interstellar medium. If we place a slit there, this is what we see. We see like a number, many molecular hydrogen lines. And with these guys, what we can do is to obtain physical properties such as temperature of the knot, column density, and there are being studies here, for example, one by Varati and collaborators back in 2015, where they measure column densities, mass of the knots, and so on. Also, if you have high spectral resolution, for example, we use ISAC VLT here to retrieve kinematic information, this is what we obtain. So, high velocities, decent mass ejection rate and momentum rate here. So you see that these things are pretty big and really energetic. Also, in the intro here, I would like to show you one of the many uses that VLT, an infrared instrument, can give it to you. So here we use the VLT ISAC to peer into G35 region, which is again another massive protostar system or region where you can combine imaging and spectroscopy to do this kind of analysis again when we measure kinematic properties. But I tell you more. If you combine it with other wavelengths, you can have one of the most complete views of a protoplanetary, of a massive star-forming region here with ALMA tracing at 800 microns. The dust continue where the stars are forming here. So you see a number of accumulation here that we believe are the driving source of the jet here that is traced by the near infrared, but also by the radio. So this is a complete view of this protostar system. And as I told you, we observe actually Brochet gamma extending more than 18,000 AU from the central source. So, we believe that it was coming mainly the high velocity from shocks and maybe the low velocity component. Remember, these are radial velocities for maybe 8 radiation from the center protostar that is actually pumping UV photons in there. Okay, but today I'm not here to talk about this. I'm here to talk about the IRAS 18264 region that we observe with integral field units with ESO. So we used two sets of instruments that on the one side we used Symphony, which here are the properties. We had like a superb spatial resolution thanks to the adaptive optic system and the natural gas star. It's got a decent spectral resolution that allows us to measure radial velocities and a small field of view, okay, because this is what we have. But we also were lucky enough to have VLT Camos, which is sort of like the big brother of Symphony. However, it doesn't have AO system, adaptive optics, but still we were super lucky because we got 0.6 arc-second in scene limited mode. So these were like super observations. But as you can see, the field of view is just super big, and that's really nice. Before I continue, for those that may not know what is an IFU, that is, if you aren't familiar to ALMA, this is a similar thing, it's a cube. So you have both images and a spectra for every single pixel. So you have an image for every single wavelength, as is shown here naively, but also you have a spectra for every single pixel. So it's a super tool that you can do many things, and I'm going to show you right now. So let me first say that this work has been done in collaboration with Ana Rita Costa. She was a summer student last year with us working in the CASM program. That is a program that we carry out in Chalmers University of Technology. Here is the link if you are more interested. These are like a super cohort of students. I'm super happy, and congratulations publicly here, Ana. She's now the grad student in Porto. So we work together on this region. And let me tell you a little bit more about it. So the region that we observed with Symphony and Clémence was, as I said here, IRAS 18 from now on, and it's located at 3.3 kiloparsecs, and it was first imaged by Barricat back in 2010. And this is what you see, which is, you see the central obscured or even saturated region here that is, we believe, the driving source. And you have here like what we believe it was bipolar outflow. It was also observed by Boither back in 2002 with the CO221 outflow here. And you see, like normal as expected, the blue shifted CO outflow and the red shifted CO outflow here. And these are our observations. So we have the big box, which is Clémence, and the small box, which is Symphony. And I'm going to show you both in a minute. Normally, Clémence is going to be on the left and Symphony on the right. Okay, so what did we see? So here I'm showing you first of all, like the continuous subtracted H2 emission. And I'm showing you this because it's the main tracer, the more clear jet tracer in high mass or in young star objects in general. Here you see we label all the different nodes here, and we can see like as expected bipolar outflow here. And again, with Symphony, since we have a little bit of better angular resolution, we could resolve things that maybe were not resolved in Clémence. And just to give you a help with your eye, this corresponds to different nodes here. It should be said that these guys has been previously reported as MHO, like molecular hydrogen objects in previous papers. But we could, for the first time, I think we're showing a spectroscopy on them. So one of the first things that you can do is to have a look at the continuum emission and the point sources. And here, for example, it becomes more clear why we need also Symphony in the central region, because the resolution is just much better. Okay, so we got like 9 continuum sources or point sources, and also bracket gamma emitters. So we could, as I said, extract the spectrum, and this is what I'm showing you here. And this could be an indication of YSOs, or at least point sources in there. Maybe some of them are foreground, background. So that's why we use also the bracket gamma as an indication of youth. Okay, so from there you see that S7 and S5 and even S6 are showing bracket gamma. So that may be an indication of their young. Also, we were able, since we have, as I said, a spectrum for every single pixel, we could do excitation maps from the integrated flux ratio of these two molecular hydrogen lines. And you can see that more or less they're reddish, greenish colors. That means there is of about 10, this ratio. What does it mean? What does it tell us? So this tells us that if the ratio are around 10, this is shock driven, as one might expect, okay? But if they are like below 3, they may be UV pumped. But it seems clear that these knots are shock driven. However, we shouldn't use only the ratio to differentiate. So we also made the radial velocity map, and this is what you see here. And this is where things start to get interesting, like weird, because this is not what we expect. If you pay attention here, you have like both lobes are blue, and this is not what one might expect. You should have one blue going towards you and one red receding against from you. And you see that velocity are quite high. In radial velocity can be even like 100 kilometers per second, okay? So what you expect is something like this. That is a previous work that we also did with VLT Symphony, where you have perfectly differentiated the blue shifted outflow and the red shifted outflow. So we needed to peer more into the details on this region. So what happens? I'm marking here the continuum sources with the stars, okay, with yellow stars. We were lucky enough to also have 12 CO from SMA, so we have a decent also angular resolution here. And you see that the blue shifted CO outflow coincide perfectly with the blue shifted molecular hydrogen in the near-infrared outflow. But you see that the red, also, sorry, I should have said, these white boxes is because we didn't have observations, okay? I forgot to say that. So when you see like black boxes or white boxes is because the observation weren't performed in there. So that was sad days. But anyway, here you see that the red contours perfectly aligns this missing redshifted outflow. So our interpretation here was that we are not in front of just one outflow, but many. And in particular, we delineate here a number of lines. So we believe that this is the main outflow here, blue one, red one, and then a secondary here, as is traced again by the near infrared blue outflow here, and also in the 12CO SMA red shifted. Okay, so basically the red shifted is not seen in the near infrared because it's obscure and the light cannot escape to the gas and dust, whereas the blue is sort of like it's being cleared and you can see it. Okay, so let me put it in context here. This is a zooming of the region just to also give you a sense of what we found in the and other people found in the literature about this region. So you have here the symphony point sources. This what you see. Also, we retrieved from the archival data 2.7 millimeters, so it's perfectly aligned with the obscure near infrared. So ALMA can reveal that. That's fantastic. And also an earlier work by Isaac 2020. They investigated these millimeter sources and they found 6 sources of them. Then also in this same paper, they also used the UMRT at 1000 megahertz to have like 2 main blobs here that may be tracing the outflow actually. And earlier work by the VLA, also like a number. You see that it is becoming a mess. Okay, there are many things here. And finally, well, there's also an earlier work by also VLA 1.6 centimeter where 3 main sources were revealed. And finally, the mid-infrared by Sikanowski and collaborators. Long story short, we think that there are 2 main driving sources as we investigated the spectral indices and such and touch. And there are 2 main outflow, as I said, driving driven by the 2 main sources. And this is for the first time, I think we see this source that in the near infrared that may be why so because we have this increasing continuum. Okay, I'm gonna finish this the result of this paper by telling you that we also fitted a spectral energy distribution using the Zanantan model grid that is based on the core accretion model. We assume, even though I have shown you many sources there, we assume that the SCD is dominated by 1 main processor. As you may see here also in the Spitzer image, that we have 1 main block. We couldn't differentiate in the infrared, in the mid infrared and far infrared different sources. Okay, so we fitted SCDs, as I said, and what we obtained was like different models that tells us that the stars are at least 4 solar masses, and they're on their way to become massive. Okay, and we can retrieve very important information such as the mass of the core, mass of its density of the clump, and others, and also the mass accretion disk of the star from the disk to the star. Okay, so in a couple of minutes, I think I'm 20 minutes now, so I would like to connect with the fitting tool that we have made. So this is a paper that I have submitted a few weeks ago, and these are the collaborators that have worked on this project. We have created an SCD tool, okay, that is based on a previous version of IDL, and now it's accessible through the pip install via, it's hosted in GitHub and PyPy. So you can Google that, but it's as simple as typing on your terminal pip or pip3, depending on your installer, SCD creator, and then you install it. So let me tell you very briefly, this will need another Hypatia Colloquium, but let me tell you the 2 main classes of SCD. So you've got like an SCD fluxer and an SCD feeder, and by its name, you can imagine what they do. So the fluxer basically measures fluxes. It's sort of like a number of convenience tools there that you can get the flux. If you have the units, it gives them in Jansky, but if you don't have them for some reason, you can do your own transformation. You can make nice plots and stuff. But if you have your fluxes, because you have your super tool and you trust your fluxes, you can fit them if you're interested in massive star-forming models. There is again like a user-friendly way to fit these SCDs, and you can get the model information, plot the different SCDs, and so on. And also would like to tell you again quickly here an algorithm that we have developed that is called get optimal aperture, because one of the first questions that you may ask is what is the aperture size that you choose to make extended photometry. So this is work done by, in collaboration also with Zoe Telpkan, who is a grad student at the University of Virginia in the United States. Basically, what we did together here was to try to come up with a simple algorithm that tells us where to put, how big the aperture should be. And this is based on a simple statement, say that if the aperture increases by a certain amount, it doesn't increase more in the flux. Okay, so this is input by the user, and you can modify it as you wish. But at least we have a reproducible way to choose the aperture, because many times it's just chosen by eye and it's difficult to reproduce. Okay, so to finish, just to show you very quickly some of the outputs of this SCD creator that has been compiled in SOMA 4. This is the paper that we submitted. And again, this is similar to what I showed you in the previous work, that we retrieve different physical information. We have done that for 40 different sources that include SOMA 1, 2, 3, and 4. And to finish, just to give you my conclusions here, is that near-infrared observations, well, I hope I have convinced you, reveal massive star formation through the jets, because very close to the center is very obscure, through their jets and the outflow cavity walls. Also, I would like to highlight that thanks to VLT, I have been able to use many of different instrument imager, spectroscoper, IFU, and it's been great to reveal massive star formation. Also, I know it's been pretty quickly, but the SCD creator provides a toolkit to perform aperture photometry and to fit different SCDs. So I'll please ask me if you have any questions. But nonetheless, we still have a lot to do. Okay, maybe this is something that we want to explore a little bit more. If massive star formation is a scalar version of low mass, both like the formation or the properties of the jet. So with that, thank you very much. Yeah, I'll take questions.
Thank you a lot for the wonderful talk. And I open the floor for questions. And I will take the privilege of being the chair, and I will ask first. So what's the age of the region you were studying, the IRS 18?
Right, so the model tells us when we feed the SCD, there is also evolutionary tracks. Sorry, I'm looking at the other screen. Okay. So it tells us that it's about between 5×10⁴ or 1×10⁵. So it's 100,000 years kind of thing. So it is young, but not super young. Okay.
I would say it's quite young.
Right.
Very young. Okay, thank you. Giacomo?
Yeah, thank you, Ruben. Can you, if you go back to basically your interpretation of the jets, basically where you showed it, because I saw a feature that I didn't exactly this plot. I was wondering, I didn't understand it. Maybe you explained it. I'm sorry, but on the middle right, so you have this blue jet, but then you have a red one at the very. So you have a blue jet, then a black. So if you go back, basically without any, so you see exactly. So next to the, so you see that I didn't understand what exactly that physics of that part. Right.
Yeah, that is actually, I didn't mention intentionally because that was a challenging one. So what we believe, this is, you see, it's a very complicated region, but if I can spend 1 minute here, I'll tell you my interpretation. So what I think is going on here, maybe actually I can even annotate. So, we have here a number of point sources, and I show you with the other ALMA data and stuff that there are things going on here. However, we didn't have any radio data ALMA in this region, but you see that there are two sources, both showing the continuum, and also, if you remember, in bracket gamma. As I said, bracket gamma is an indicator of youth. So we have two ways to see this. So either this star is driving this jet here, and this is plausible because the bow shock is in this direction, or we have the other star driving this outflow here. However, this is a little bit more complicated for me to understand because the outflow is in the other direction. You know the way the outflow of the bow shock. So you expect the bow shock to be rounded in the direction that is going, if that makes any sense. So I think we actually didn't know what was going on in here, but most likely this source may be driving this this outflow here, and maybe, I don't know, maybe other, in other directions. So the thing is that this region is super complicated. There are many sources, and tying one source to the other is quite difficult.
Yeah, because you were describing this situation in which you have basically, let's call it blue and red on the opposite side with respect to the origin source, right? This is
right.
Depending on the orientation probably of the jet. I can imagine.
Yep. Inclination.
Because I see, well, you have this red one. I mean, you have a kind of on the edge of your observations on your CHAMOS mosaic. You have basically a blue part there,
right.
the right hand side. So it looks like more because it's I don't know. It's really interesting, actually. Yeah.
The thing is also, I didn't show here for lack of time, but in the paper we show that there is a radio source in this region. So that is also an indication that there may be another YSO here messing with the region, and you see also that the morphology here, this follows this direction, maybe this follows the other. So we may sort of like the most simple explanation that there are two main sources, one here and the other there. But it may well be that there are more sources, more outflows. But this is something that we will need more angular resolution to discern.
Okay. Fascinating, yeah. And I wanted to mention something just for fun, but I mean, you mentioned a few times, you say, we were lucky to get this. I mean, this is not luck. I mean, you applied for time, you got selected, so it's congratulations. I mean, all this data requires, work and, so
thank you. Thank you.
No, I understand your spirit and I like it. Just I want to say this is a huge amount of effort.
It's a huge, because it's not only the observation, but also the observer, the telescope. I mean, when you come to appreciate all this work, and you're really humble here. I mean, it's a lot of work. Good.
Thank you very much. Thank you.
Thank you, Giacomo. Yeah, indeed, it's a beautiful dataset. And since you are in this slide, I have a question, because the velocities you are showing here of the outflows are, let's say, of the limits of CHAMOS resolution. So I wonder if the fact that I cannot distinguish between because this is a very complicated picture, would it be, if you had observations with higher spectral resolution, would that help you to distinguish?
Absolutely, yes. Yeah, absolutely. Actually, we have done previous work here that I didn't have the time to show, but we had symphony data, for example, and then we have follow up with ISAC at 10,000 resolution, which is about 30 kilometers per second. But even I tell you more, we have with CRIRES, which is like 100,000 spectral resolution. So definitely, yes, we just need to apply for it and get it. But the only problem though is that, as you know, these are long slits. So it's like you have either imaging or spectra, a higher resolution, but both, as CHAMOS is giving us, this is what we're pushing the limits of the instrument. But yeah, as you well have said, this is at the limit of the resolution. However, since these lines are really high signal to noise, we can push a little bit more the limits of that spectral resolution.
Yeah, so I wonder, what was the integration time here? More or less.
It should be like 300 seconds per shot, but it was a total of like 3,000, because to make the mosaic, you have to combine many times. It's about, say, like with overheads and stuff, it's about 2 hours long. I mean, raw thumb estimation.
So maybe if you had more deep observations, you could also observe the redshifted outflows here.
Maybe. So this is something that we actually, I have also to say that we got, in the last semester, we got more CHAMOS data on other sources. So I'm looking forward to reduce those and to analyze them, because they should be even better than this, which is difficult to believe. But yeah, I hope to come next year and tell you about it.
Yeah, sounds exciting. And tell me, how did you reduce data? Did you use the standard pipeline? Because I saw that your spectra are really nice without any telluric features. How did you do that?
That was a great job by the student, by Anna. But we made a combination. So we used gas Ganon, we also used the ESO reflex, but then we also had some Python script tailored that we kind of like polish a little bit more. For example, all the telluric correction, we did it ourselves because we weren't super happy with the result from the pipeline. But I think it's also because this data is actually science verification data from Susan Ramsey, that she's one of our collaborators. So I need to have a look at the new data, and hopefully the pipeline will give me like nice and clean data set. Nonetheless, if not, we have our own custom scripts to follow that up.
That's amazing. Congratulations. Okay, I don't see any more questions. So thank you very much once again for wonderful talk. I'm very much excited about it. And I'm looking forward to hear more about and to read more about your new code. Thank you.
Thank you very much.
Good. Thank you, Dominika. Thank you, Lukáš. So, and of course, thank you to Rubén and Clémence for the beautiful talks, and congratulations again. Good luck for your career, of course, for your upcoming success. I hope to see you in person soon, but I'm sure it's going to happen very soon. So thank you very much again. And with this, I would like to thank also our attendees, and for everyone, please be aware that there is a program online. You can go and download the CVs of our speakers. You can also see from the moment the proceeding of the Hypatia Colloquium 2021, but there will be a new, which is this beautiful, proceeding book. But you can, if you go, there will be a new one coming out during the summer for the 2022 series. And with this, I would like to thank